Welcome to Characterization Sheets in the Donahue and Pigza Research Labs. This set of videos will guide you through filling out one of these data sheets, so then that way we will have all of our data recorded and in a meaningful way. So as you see here at the beginning, the first line is notebook. This is just your batch number. So whatever number you gave your reaction, this is the number that will go here at the top. Each of these boxes correlates to a different set of data that you can collect for that compound, and you will check each of these boxes that you have. So you can imagine this to say, do you have a TLC already taken? If yes, check the box. Have you taken an IR of this solution, of this compound? Yes, then check the box. Have you taken an HPLC? I have not taken an HPLC of this, so I will not be checking the HPLC box. There. So all of the boxes that we have data for are now checked. Moving on to the IUPAC name. We are not expecting you to be able to name these by yourself. There are a couple of ways that you can do this. One, you can use ChemDraw Professional in order to type your compound in, and then do the convert to name function. Or you can go online and search your compound on SciFinder. Or if you're in the Donahue Research Lab, our lab notebook that we use online is through Perkin-Elmer and will name the compounds for you. So you can get your IUPAC name through any of those sources, and all of them will be correct. There. So now that we have the name, we'll move on to the next box. The in-sheet code we're actually not going to write out. This is something that we will use in the digital version, so we're going to skip this box for the time being. The CAS registry number is the number given to each compound from the Chemical Abstract Service. This registry number, if you go to SciFinder and build your compound, you will actually, if the compound is known, you'll get a CAS registry number, but if it is unknown, it will not have one. An exception to this is that sometimes a compound will be known but not necessarily have any sources. We'll go ahead and we'll put the CAS registry number since our compound is known. Alright, there we go. So now we're going to move over to the reaction and product structure. So throughout this process, we are going to be assigning the carbon and proton assignments to our compound. But first we have to start by drawing out the reaction. Like so. As you see here, I've tried to actually make my transition or transformation similar on both ends. So as you see, I have the triisopropyl group at the top right of my structure, and I have it at the top right here. This is just so that way, if I look at this reaction, I don't have to do a lot of mental gymnastics in order to determine what the transformation is. As you see, I have put this in the presence of a base and then cyclized this. So then we move on to the carbon-13 multiplicity. So this is something that we will actually have to look at our structure, and we're going to predict how many singlets, doublets, triplets, and quartets we would find. So when we start off, we can look at this carbon-13 multiplicity, and we see 1, 2, 3, 4. So our theory here is going to be 4. Doublets, we have 1, 2, 3, and we don't have any down here, so we have 3 doublets. Triplets, we don't have any up here, but we do have 2 down here. And quartets. So 1, 2, 3, 4, 5, 6. And then we add that all together for 15. We'll come back to this section after we fill out more of our paper, but for right now, that's all we're going to do on that section. So then when we get down here to the latter portion of it, you see we have carbon-13 and proton NMR assignments. So like previously, we do have boxes that we have to check. So this compound was ran in chloroform, so I'm going to go ahead and check the chloroform box. So what this data portion is for is we were actually going to put a letter to each of our carbons. So when we get our carbon, this is what it should look out like. So this is our normal carbon-13, this is our carbon-13 depth 135, and this is our carbon-13 depth 90. So this, you can think of this having all C13s. So this will have singlets, doublets, triplets, and quartets at it. The depth 135, if you want to think of it as everything up, will be your doublets and your quartets. And everything down will be your triplets. On the depth 90, the only thing that it shows is up, and these are doublets. So as you see, it's easy for us to determine the multiplicity of a carbon-13 by looking, and if, say for instance this one, this is our only triplet. If we look here, if we are missing peaks from our carbon-13 depth 90, but we have them down here, we label them as quartets. So let's go ahead and we'll label them according to how we have it on the sheet alphabetically. In the Donahue and Pigza Research Labs, we start here at the far left, and we label that first peak A. And we will continue on. There. So, what we will then do is we will take peak A, and we will look at the number associated with it. We will then go back to our data sheet, and we will use that number in the A column. So the delta C of A is 153.4 for this compound. And the multiplicity, well, we don't have anything in our carbon depth 135, and we don't have anything in our depth 90, so that means that this is a singlet. We'll continue this process for all the rest of the carbons. One thing that I want to mention about doing these characterizations is make sure that you always do them in pencil, because you may mess up, whether that be putting down like a wrong number or putting down the wrong multiplicity. So please just make sure that you do these in pencil. So as we continue on, you can see, so 151.155, I am just going to put 151.2 because I am just rounding that 1.5 to 2. So 151.2 is what I put. So as we see, B has nothing in the, as you see, there you go. So as you see, B has nothing in the depth 135 or the depth 90, so this is a singlet. Continuing on, as we see now, C is at 131.3. Nothing in the depth 135, nothing in the depth 90, so that's a singlet. Moving over to D, D is at 123.8. So now we have something up. So if we remember, up means either a doublet or quartet. So then we have something up in the depth 90. So that tells us that this is a doublet. We do not deal with this peak at 77. So something to mention here is that this is deuterated chloroform. So do not integrate or peak pick, or you do not have to deal with that peak. So then when we look at E, E is at 34.2. Same thing, we have a peak up, we have a peak up. This is a doublet. F, so you can see we have it at 29 point, so that is 7.8, so I'm going to go ahead and round up to 29.8. And since we have a peak up and up, I'm going to make this a doublet. G is at 27.098, so 27.1. This one, I have a peak that is down. I have nothing in my depth 90. This is a triplet. Moving over to H. H, I have 24.9. As you see, I have something up, but I have nothing here in my depth 90. So this one is a quartet. And last one, I have 23.5, so 23.6, and that is a quartet as well. So, as you see, we've been able to start filling out some of these boxes. We've been able to talk about our notebook number and naming our compound, being able to check all of our necessary boxes off. We have written out the reaction. We have talked about the C13 multiplicity, and we have talked about labeling the carbons and being able to list their multiplicities as well. Tune in for the next video for HSQC and correlating your protons to their carbons.